Okay, to recap, we said the solution of a system of two equations is when you find a point that satisfies both, which means you're finding the intersection point, the points where the two lines intersect, or two curves, because they might not be lines. So we're going to solve the following systems by graphing them. Yes, there are other methods. This is going to be by graphing. So first thing you're going to have to do is graph both of these equations, and hopefully you recognize, since they're both in y equals mx plus b form, they're both lines. Cool. So for the first one, you start at 1, positive 1, and you're going to go down to right 1, down to right 1, because that's your slope. Well, let me get you a picture. So you start at 1, right there at 1, and you go down to right 1, put a dot, down to right 1, put a dot, and so on. You also could go up to left 1, up to left 1. Then you also want the line 3x minus 4, which means you're going to start at negative 4, and you're going to go up 3, right 1. And there that one is. And you can see that the two of them intersect at, well, hopefully you can see, they intersect at the point 1, negative 1. Get rid of all this. Boom. There it is. Okay. So our solution is 1, negative 1. Poof, there we go. So I pasted it in. So our solution, which is what we were really looking for, is 1, negative 1. It's not enough just to graph it. You also have to write the solution. It's only fair. Okay. Now what about the next one? Okay, so we have to start at negative 3 and go up 1 over 3, up 1 over 3, up 1, right 3. So I bring up my graphing program again. And it's right there. Well, I don't like how light that is. I'm going to make it green again. And then the other one was right here. Make that maroon again. Actually, I like that deep blue. There we go. And you can see, hopefully, that these are never going to meet, right? And hopefully you could spot that right away. See how they both have a third? So your solution is the empty set. There we go. There is no answer. The empty set, the null set, there's no solution, right? Because, and I'll put it, because the lines are parallel. They will never intersect. Okay. Next. All right, what about down here? Well, you're in a little bit more of a pickle down here because that second line is not actually in the right form for yourself. So you got to change it around a bit. You're going to have to subtract the 6x from both sides. All right, and that leaves you minus 2y is equal to minus 6x plus 4. Okay, real quick, these are not like terms, so you can't combine them together and make it negative 2. One has an x and one doesn't, so they're not like terms. And then you also have the added issue of we like to go mx plus b. So put the x1 in front and the b1 in back. And then we divide by negative 2. Oops. All right, so over here, no problems, going to disappear. Right? Because negative 2 over 2 is 1, so it's 1y, which is y, equals, now negative 6 over negative 2 makes positive 3. So it's 3x minus 2, because you have to divide both of these things by negative 2, not just one, not just the other, but both. Right? You're really taking, if you want to see it, you're really doing negative 6 over negative 2x plus 4 over negative 2. Right? That's what you're doing. And that gives you this. But notice, it's the same equation, right? Okay, so you have one equation at 3x minus 2, and then you have another equation at 3x minus 2. And if you'll notice, they don't look that different. That's because they're the same line. Right? One is laying on top of the other. Okay. All right, so let me copy and paste. All right, so what's our solution then? If their two lines are lying on top of each other, then what we want to say is all the points on the line are the solution, right? Not all points. So some teachers might have taught you like all numbers. No, it's not. I know what they're getting at, but no, it's not all numbers. It's all these points. So the fancy way to say that is to say every point. So you put little curly braces, sorry. These ones. You say, okay, all the x comma y, all the points are in xy form, such that y is equal to 3x minus 2. Right? That is the fancy way to write all the points that are on the line. So you can see it, all the points on the line. You can see all the points on the line. Actually, I should say, be very clear. On the line, y equals 3x minus 2. That's the actual answer. Right? All the points that are on that line. So that's the way to write it out in English. This is one time where English is actually a little bit quicker than writing it out in math speak, in math terminology, which is the symbol notation down here. Okay, you've just learned a valuable lesson, though, is that there is more than one way to do this. All right, so when you have linear systems, and again, linear are not the only systems we're going to work with, but they're the ones we work with the most often. There are three kinds. And it's shown up here in these three figures, and I also showed them right here in this example. So there's something called a consistent system, a conditional system. It's got one solution, one intersection. Obviously, that's the one you're going to see most often. Right? The lines intersect at one point. Sometimes it'll be more than one point, but it'll be like 2 points or 3 points, like if one of them is a curve. But for linear, it can only be 1 point. That's this one. Or it could be inconsistent. Right? That's this one, where they never meet. The lines were parallel, they never met. That's an inconsistent system. Or a dependent system. The lines are identical. One is lying on top of the other, so every point on that line is a solution. Right? Those are the three types of linear systems you can have. So when you're answering a question for linear systems, you're either going to have a point, like this. You're going to have no solution because they were parallel, or you're going to have all the points on the line are a solution, because they were dependent. So if you like, this is an inconsistent system. This is a one solution system, using the terminology from this book. And this one is a dependent system. System meaning two equations. This little thing originally that I gave you, that's got two equations in it, right there. Oh, no. There, that part. Two equations. When you do that with two lines, you're either going to be one, none, or lots, infinitely many. All right, let's use this table below to solve the system. Well, solving the system means that, hey, the two lines have the same value, right, for x and y, right? In other words, they both had the same point. For example, if you look at this, the green line had 1, -1 in it, and the red, maroon line, whatever, had 1, -1. They both had 1, -1 in them. Now, you could see it graphically, right? You could see it on the graph, but how could you see it in a table? Because remember, we always want to keep all of those things in mind. We always want to be able to do tables, graphs, and the algebra, and that's algebra parts coming in the next section, right? So graphs are pretty easy. Once you know how to graph, you just got to graph real carefully on a grid. And to be honest with you, tables are pretty simple too. So if you look at this table, you want to say, okay, I've got one line here, one line here. You know what, let me graph those two lines so you can see it. Hold on one sec. Okay, here's the line, -4x plus 21. You can see I'm starting at 21 up here, and I go down 4 over 1, down 4 over 1. And what they're doing is they're not showing you the line. They're showing you these, oops, maybe I'll make them the same color, these points from the line, right? So instead of the line, they're just showing you those points, but in a table form. So it's 0, 21, 1, 17, 2, 13, and so on. So there's one line in those dots. And they only went from 0 to 4, so I stopped right there at 4. And then they're doing it again for this other line, 5x plus 3. So let me show you that. Hold on. There we go. So there's the line 5x plus 3. See, it starts at 3 down here right? There's the intercept. It goes up 5 over 1, dot, up 5 over 1. And so they're putting those dots in, 0, 3, and then they're taking away. So all you're looking at is the dots. You're not looking at the actual lines, right? The lines look like this, but you're not looking at those, right? See, these are both linear equations right there. So they're not having you look at those, they're having you look at the coordinates for the dots. So it looks like that. Let me copy and paste this in real quick. Make it real small. There we go. So that's kind of a picture of what's happening. And then you can see what's going to happen is the red dots and the purple dots, and of course this computer program can't show that, but they're on top of each other, right? At this spot right here. So the question is, what is that spot? Well, it's over 2 up 13. You can see it in the graph real simple, but you can spot it right there. See it in the table? Hold on, let me give it, ooh, I'll make it black. Oh, nice. There we go. So you can see that 213 business right there, that's that black dot where they intersect. And you didn't have to draw a picture. I was just drawing a picture to show you what was going on. But the solution for sure is 2, 13. And you did not have to do all this rigmarole to find that. I mean, it was pretty obvious what it was going to be from the table, but I wanted to show you why it was working that way, because sometimes students look at that and they get a little confused. And they're thinking, what? What are you talking about? Well, all we're talking about is a table of some graph. You just don't get to see the graph. So if you had that graph, you could spot, oh, it's 213, right? But you don't have to see a graph. Look, watch, it's gone. There you go. It's still got to be 213 because it's got to be where those suckers intersect, right? Where the two y values are the same. Must be where those graphs are the same. All right. And we're done with this section. So I hope you've enjoyed section 3.1. We'll meet you back here for 3.2, which is where we start doing the stuff with algebra. Instead of looking at graphs, instead of looking at tables, how could we solve this using just the equations with x's and y's? That's algebra. All right, I'll meet you back here then.